Awesome. Thank you, Ralph. Yeah, thank you all for coming. As Ralph said, I'm Jatin. I'll be talking today about comparing some virtual analog modeling techniques. Let's see, can I move through these? There we go. All right, yeah, so just a little bit about me. I'm a musician. I've worked as an electrical engineer. I've worked as a mixing and mastering engineer a little bit. And for the past few years, I've mostly been at CCRMA studying audio signal processing and related things. For the past maybe 5 or so years, I've been making audio plugins and DAWs and similar software, both as a hobby and professionally. And I wanted to give a little disclaimer here. So I'll be talking a lot today about guitar and guitar-related things. But I'm not really a guitarist. I play piano, I play saxophone, and I'm trying to learn guitar. So there may be a few guitar-related things that I don't understand too well, but I'm trying to understand them better and continue learning there. So for me, this project kind of started when I started reading about this guitar pedal called the Klon Centaur. This was designed and built by a fellow named Bill Finnegan from MIT from maybe the mid-90s through the early 2000s. And I was very kind of amazed by the way that people talked about this pedal, about how they said, oh, it's distortion, but it preserves kind of the tone that your sound already has. So it distorts your sound without changing the tone. And I found that very interesting. And I was very curious, like, well, what about this pedal makes it sound like that? And so after kind of reading about it and thinking about it for a while, I decided that I would try to make what you might call a virtual analog model of this pedal. So a little bit about virtual analog modeling, or VA modeling, as it's sometimes abbreviated. The basic idea is that you take some analog audio gear, so maybe that's a piece of rack mount gear or a Eurorack module or something like that, and you want to create a digital emulation of that piece of gear. And there's a bunch of reasons why you may want to do this. Maybe this gear is old or it's rare. Maybe it's very expensive, and so your digital version can be much cheaper. The Klon, for example, is like $3,000, I think, for one of the original models. So definitely an emulation could probably be made for much cheaper. Oftentimes it's convenient. So if you have some rack mount gear, it's typically not very portable or anything like that. So if you have a digital version that you can keep on your laptop or something like that, it's a lot more convenient. And for me personally, I find that kind of going through the process of making a digital emulation helps me understand what makes these effects sound the way they do. And that's something that I really enjoy, is trying to have that better understanding. So when you're talking about kind of circuit modeling and analog modeling, there's a couple different paradigms you can start from. One is called white box modeling. The other is black box modeling. Or you can kind of do a combination of the two, which some people call gray box modeling. So the idea for white box modeling is that you think of your system as the sum of whatever component parts make up that system. And those parts have some physical properties, and you want to model the kind of physical interactions between each part. So for circuits, this is typically the resistors and capacitors. And you want to model some of the interactions between the voltages and the currents of these different components. And there's a bunch of ways that you might want to do this. I've listed a few of them here. Some of the advantages of white box modeling is that you typically get very accurate modeling of your circuit behavior, even in kind of extreme situations. Maybe if you kind of go beyond what might be realistically possible with this thing that you're modeling, you can typically get an accurate model of how the circuit might respond to something outside of physical reality, just because the physics modeling still holds up, kind of going beyond the real world physics that we have to deal with in the analog world. Another advantage is that if you have control parameters in your circuit, like switches or knobs, those are pretty easy to include in your white box model. You don't have to work too hard. You can just change your resistor value or something like that, and have that be your model of these control parameters. One of the big disadvantages is that running these physics simulations in real time can be computationally expensive. So that's something you need to think about as far as what you can model with your white box techniques. On the other side, you have black box modeling, where you don't really care at all about what makes up the system on the inside. All you care about is just what it sounds like and like what the inputs and outputs sound like. So typically what you do is you would take your circuit or whatever gear you're modeling, and you would give it some input signal and you would measure the output. And then you would figure out some way to recreate that measured output using some signal processing techniques. So the most kind of common example for black box modeling is impulse responses. So if you want a room reverb, for instance, sure, you can model the way that your sound reflects in a room and kind of the physical properties of your room. But that can be very difficult, especially for very complicated rooms and room geometries and so on. So the black box approach would be to just record an impulse response, and then you can use that to create a convolution reverb. Unfortunately, impulse responses only really work for linear systems. So for nonlinear systems, we have these other techniques we have to deal with. In this talk, I'll be talking a bit about neural networks and how in recent years people have started using neural networks for black box modeling. Some of the big advantages of black box modeling: if you have some kind of unique behavior, maybe your piece of gear sounds unique in some way that other pieces of gear don't, or in general, if you have anything that couldn't really be learned from the circuit schematic or something like that, black box modeling is usually better at capturing those types of things. Oftentimes, these methods are computationally cheaper. However, it can be difficult to include control parameters, so knobs and things like that can be difficult to include in your black box model. So let's say you've gone through and you've made your digital emulation of some analog gear. What are you going to do with it? Well, typically people will make an audio plugin. And kind of the platform that you're going to be running on for an audio plugin is you'll have some consumer grade CPU, just something that you could find in a standard laptop or desktop machine these days. If you have lookup tables or things like that your plugin relies on, you'll have more than enough memory to store those things, so it's not really anything to worry about. But you will have to share resources with other plugins. So no one's going to open up Ableton or Pro Tools and only use your plugin. They're going to use your plugin plus 20 or 30 more. So you need to share those resources. Kind of another approach would be to make some embedded audio system. So maybe this is a guitar pedal or a synthesizer module or something like that. In this case, you kind of get to choose your processor. So you can choose what platform you want to run on, but the more powerful of a processor you need, the more expensive that's going to be. So there's a bit of a trade-off there. Typically in this situation, you will have somewhat limited memory. So if you have a lot of lookup tables or neural network weights that take up a lot of memory, you have to be careful with where you're going to store that and what embedded device you're using. That said, one of the advantages is that typically you don't have to share any resources. Pretty much the only thing running on this embedded device is going to be your algorithm. So that's kind of a nice advantage there. So when I started working on this project, my goal was to create a digital model of the Klon Centaur using different circuit modeling methods for different subcircuits from the pedal. So something that I've noticed in the academic world is that people get very fixated on one circuit modeling method, and that tends to be kind of their main area of study. And this can be good for kind of developing these methods and improving the circuit modeling methods that we have. But when you're just trying to make a really good model of some circuit, oftentimes the method that you choose has to be more dependent on the circuit itself and what the circuit needs and what method the circuit is most suited for. So that's something I was hoping to kind of prove through this exercise is how different circuit modeling methods can work better for different circuits. I was also hoping to have some desktop and some embedded implementation of the effect, and I wanted to see how the different circuit modeling methods kind of compared and contrasted for these different implementations. So just a quick outline of what I'm going to be talking about today. I'm going to go through a few different circuit modeling techniques and kind of use a different subcircuit from the Klon Centaur for each technique as kind of an example. I'm not going to spend too much time on these traditional circuit modeling techniques since there's like textbooks and plenty of literature about that already. I did want to spend a little more time on the neural network side of things since that's a bit newer and there's not as much out there in the world right now for that. Then finally, I'll present the desktop and the embedded implementations and show some results. I think there was maybe a raised hand or something here. I don't really know how to see that. Okay. Yeah, if you have a question, just pop that in the question and answer box up there, and I'll stop at a few points along the way of this presentation to answer questions. So definitely feel free to ask questions in the Q&A box. Okay, one sec here. So the first circuit modeling technique that I wanted to talk about is nodal analysis. So nodal analysis is one of the simpler and more kind of straightforward circuit modeling methods. And if you're just getting into circuit modeling, this is probably going to be one of the techniques that you're going to learn about. So as an example, this is the tone stage from the Klon Centaur pedal. It's basically just a high shelf filter, and there's this potentiometer here that is connected to the tone knob on the faceplate of the pedal. So in nodal analysis, we typically start by looking at the circuit in the continuous time domain, specifically in what electrical engineers call the Laplace domain, where we come up with this Laplace variable, S equals j omega, is usually how they define it. And then you define your impedance for each circuit component, so your resistors and your capacitors and so on, as some function of the Laplace variable. So for example, your capacitor impedance is 1 over your capacitance times S. Then you would go through and formulate this thing called the transfer function in the Laplace domain. This technique, or this kind of process, is a little bit involved and typically would be taught in a linear circuits theory textbook or something like that. So I've linked here to the textbook that I learned from, but almost any linear circuits textbook would show you how to kind of go through creating this transfer function. So once we have our transfer function in the analog domain, we want to be able to discretize it into the digital domain so that we can implement it as a digital system. So there's a number of ways that you could do this, but the most common way is to use this thing called the bilinear transform, which is what I've shown here. So basically, you take your S term from the previous slide, and you replace it with this expression here. So this expression is 2 over t, where t is your sample period, and this z to the -1 term represents a 1 sample delay in the digital world. So basically, you've transformed your transfer function from the S plane, which is analog, to the Z plane, which is digital. And then once you have your transfer function in the Z plane, we should be able to implement it with some digital filter, which is something like what you'll see here, where you've got some delay units, you've got some additions, and you've got some multiplies. And between those three things, we should be able to implement any linear digital system that you would describe with a transfer function like that. So a few things to think about when you're going through this discretization process of going from continuous time to discrete time or to digital time. The first is frequency warping. So in the analog world, we think about frequency as being this y-axis on this plot here. I hope you all can see my mouse okay, otherwise this might be confusing. But yeah, so you can see this y-axis here as the frequency axis. And then kind of everything to the left of that is your region of stability. So any resonances in this region will be stable, and any resonances outside of that region will make your system unstable. So when you go through and you discretize your system, you basically take this infinitely long y-axis here, and you curve it so now it's mapped around the unit circle here. So your frequency axis, which was this infinitely long line, is now this finite half circle. And so when you do that, you end up warping the high frequencies. So some of the high frequencies may not be exactly 100% accurate to what you would expect them to be in the analog domain. And so that's something you need to correct for. And there's some methods for doing that, which I'm not going to get into here, but it's just something to watch out for. And then you'll also notice that the region of stability now becomes the inside of this circle. So any resonances inside this region will be stable. Any resonances outside will go unstable. So yeah, this is kind of a brief talking about a couple things to watch out for when you're discretizing a system. There we go. Okay, so if we go through this process for the tone stage from the Klon Centaur, we can actually implement this as a digital filter, and we can compare the frequency responses of the digital filter to the analog filter. So this is for various values of the tone knob here. We can compare the two frequency responses, and they look pretty accurate. So that's kind of a good way to validate that our digital model is accurate to the original analog circuit. So just real quick, some advantages and disadvantages of using nodal analysis. It's pretty simple and it's pretty computationally efficient once you get your digital model made. So most of the other circuit modeling methods that I'll be talking about after this are not quite as efficient as nodal analysis in the real-time implementations. So that's definitely an advantage of nodal analysis. The big disadvantage is that with standard nodal analysis, you can't model nonlinear circuits. So if you've got diodes or transistors or any nonlinear elements, nodal analysis in the original form can't handle those circuits. But if you extend to use this thing called modified nodal analysis, then those circuits become tractable. So that's kind of a nice addition, but you have a lot more complexity when you use modified nodal analysis. Also, sometimes not in a circuit as simple as this, but in more complicated circuits, sometimes if you have a parameter change, so for example, if you turn a knob or something like that, you need to recompute a lot of the elements of your system, sometimes even doing a matrix inversion or something more, some more involved operation like that. So that's something to watch out for. Okay. Before I move on, any questions about nodal analysis? Okay, well, if not, then I'll move on. But yeah, there will be a couple more spots for questions, so feel free to ask them. Okay, so next I'll be talking about wave digital filters. Wave digital filters have been around for 20 or 30 years now, maybe even longer. But they've only kind of recently gained popularity for modeling circuits and things like that. So yeah, there's been a lot of big advancements in the last maybe 5 or 6 years that have made wave digital filters more popular for circuit modeling. So in typical circuit modeling or in circuit analysis, we look at things in what's called the Kirchoff domain, where you think of each circuit component as having some impedance and some voltage going across the component and some current going through the component. And then we connect these components in series and parallel and so on. And this is typically how people think about circuits in most cases. However, in wave digital filters, we kind of ignore the Kirchoff domain and look at things in what's called the wave domain. So in the wave domain, we think about circuits as being made up of wave ports, and each wave port has an incident wave going into the port and some reflected wave coming back out of the port. And so typically what you do is you define some wave variable, which I've shown an example here. And the wave variable allows you to translate from your voltage and your current at some wave port to the incident wave and the reflected wave. So then you think of each circuit component, so your resistors and your capacitors and so on are what's called a one-port element with an incident wave and a reflected wave. And then you connect these components with these series and parallel adapters that connect all of these wave ports with a scattering junction. And this might seem like a completely unnecessary addition of complexity that we don't really need. But the advantage of going through all these steps is that you end up with this free parameter, which is the port resistance. So each of these series and parallel adapters will have one free parameter or one free port resistance that you get to choose. And mathematically, that's a really convenient thing to have, and it allows you to have a lot more flexibility in your modeling scheme, which I'll talk about more. So originally, wave digital filters were developed by this fellow named Alfred Fettweis in the 70s and 80s. He basically figured out that you can do you can analyze your circuits in the wave domain. And one nice thing about this, one big advantage of having this free parameter that I talked about, is that you can discretize each circuit element independently. So with nodal analysis, we had to look at the entire circuit and then discretize the entire circuit at once. In wave digital filters, you look at each element, the resistor, the capacitor, the inductor, and so on, and you discretize each element by itself, and then you can connect those elements in the wave domain, or in the digital domain, sorry. So this is really convenient because it allows us to swap out resistors and capacitors and so on in the digital domain, and we don't really have to care about kind of how the wave digital filter reacts because we know that it'll handle everything correctly so long as the conditions that I've mentioned are satisfied. So basically what he figured out is that you can create this binary connection tree between these circuit elements in the wave domain, and that allows you to do real-time circuit simulation. So as an example, this is the feed-forward network 1 circuit from the Klon Centaur. This is a very simple circuit. Sorry about that. But if we go through and we look at the binary connection tree for this circuit, it looks something like this. So you have some input voltage source, and that's connected to a series adapter here. And the series adapter is also connected to a capacitor and another series adapter. And then that series adapter is connected to a resistor and a parallel adapter. So as soon as you're able to kind of formulate this binary connection tree, then you're able to kind of run your wave digital filter simulation and get some real-time values for what that circuit might be outputting in the analog world. So again, we can kind of construct our digital model and compare that to the analog reference. So this is the response of the feed-forward network 1 in the time domain compared to the analog reference. And again, it seems to look pretty accurate. So thinking about some of the advantages and disadvantages of WDFs, the big advantage is modularity. So unlike pretty much any other circuit modeling framework, you can swap out your circuit elements and even change your circuit topology on the fly, and the wave digital filter will react in a reasonable and understanding way. So that's really nice and opens up a ton of possibilities for things like modeling circuit bending or doing real-time circuit design and things like that. That are very specific and unique to wave digital filters. Another nice thing with this kind of modularity aspect is that you can discretize each component independently, even using a different conformal map. So let's say you wanted to use the bilinear transform for one capacitor, but then for another capacitor, you wanted to use some other transform. Wave digital filters will allow you to do that, and pretty much no other circuit modeling technique would allow that. One of the big disadvantages is that there are classes of circuits that wave digital filters cannot model, at least in their traditional form. So if you have more than one nonlinear element, or if you have this type of topology called an R-type topology, then your wave digital filters can't model these circuits. In recent years, these things called R adapters have been introduced and added to the wave digital filter literature. And with R adapters, you can handle multiple nonlinearities or R-type topologies, but you also have a much greater complexity to deal with in constructing your wave digital filter. So again, it's a trade-off between flexibility and complexity. So I've just scratched the surface here on what wave digital filters are and what they can do, but I wanted to point to some more literature. So if you're interested, you can check these resources out. So Alfred Fettweiss's paper from, I guess, the mid-'80s here is a great reference for kind of the history of wave digital filters and kind of the original derivation of how they came to be. For a bit of a more modern derivation and a modern introduction, Kurt Warner's PhD thesis is really nice. He kind of brings up wave digital filters from scratch in a pretty readable and not too technical way. He also includes a lot of the more recent advancements. So if you're looking for something just to kind of bring you into wave digital filters at a low level and then gradually introduce you to the more complicated stuff, this is a really good resource. For an example of kind of the independent discretization that I was talking about, Francois Germain in his thesis has an example of discretizing circuit elements with this thing called the alpha transform. So basically, he discretizes every element in the circuit with a different transform and shows how, for some circuits, you can get a much more accurate simulation that way. And then finally, Jingji Zhang and Julia Smith have this paper where they model a really large tube amplifier circuit with wave digital filters and get a really nice sounding real-time emulation of this very complicated circuit. So if you're kind of curious how far wave digital filters can go into really large and complex audio circuits, this is a really nice proof that that wave digital filters can handle circuits of that size. Okay, so before we move on, let's see what questions we've got here. Sorry, I'm going to drink some water.
Go ahead. Do you want me to read these questions? I'm not sure they pertain to what you just presented, but you go ahead and read them, Jatin, and then.
Sure. Here, I'll go ahead and answer this one first. Sorry, my throat is kind of catching today. Okay, so first we've got this question. What does the workflow look like for creating binary connection trees describing circuits including nonlinear components like transistors, diodes, and op-amps? So really quick about transistors and op-amps. Transistors and op-amps have multiple kind of inputs. They're a little bit different from like a capacitor and or a resistor where you just have two terminals. And so because of that, traditional wave digital filters can't handle those circuit topologies. So for an op-amp or a transistor circuit, you typically need an R adapter, or sometimes there's a few other tricks you can use to get around that. But oftentimes you'll need an R adapter for circuits like that. But diodes and other things like that can be modeled with wave digital filters without too much difficulty. Actually, later on in this talk, there's a circuit with a pair of anti-parallel diodes that you can use wave digital filters for. So I'll point that out when we get there. But this is a great question because when you're formulating this binary connection tree, it's very important to think about what component gets put at the root of the tree, which is here. So kind of what I mentioned with having that free parameter. So whenever you have a series junction like this, you get one free parameter that you can choose, one port resistance that you can choose. And so typically what's done is you construct your tree so that it flows down from the root. And so when you construct your tree, you choose your free parameter in this series adapter so that no wave is propagated back up the tree. So waves are only propagated down and never back up the tree. So this is what allows you to kind of swap out these components without having to worry about recomputing the whole thing. And so the reason why the root is so important is because you're allowed to put one non-adaptable element at the root of the tree. So in this case, this is an ideal voltage source. So ideal voltage sources, ideal current sources, and nonlinear elements are non-adaptable. And so that's why they need to go at the root of the tree. So if this were a nonlinear circuit, I would have to put my diode at the root of the tree. And that's why you can't handle more than one nonlinear element, is because you only have one root for your tree. And so it can be difficult to deal with that if you were to have more than one. Okay, hopefully that answers that question. So Will R asks, what books would you recommend if you're getting started with this stuff? For R adapters specifically, the papers I mentioned at the end are really nice. For nodal analysis, I think this question was asked around the nodal analysis time. So for nodal analysis, a good linear circuits textbook would be nice, just to kind of get introduced to a lot of the kind of the circuit theory that you need to know. And then Julia Smith's physical audio signal processing textbook is really, really good for kind of the bridge between the circuit theory and the digital signal processing aspects of things. Okay, I'm just going to do one more question now so that we can keep moving, and then I'll answer more at the end if I have time. So Nick asks, how much for performance hit do you get with the R adapters, and have you done this with any success? So R adapters don't intrinsically add a ton more overhead as far as performance. The main issue with R adapters as far as performance goes is that if you have parameter changes, so if you move a knob or something like that, typically you need to do a matrix inversion whenever you move a knob. And so that's where the real performance overhead comes from. But as long as there's no parameters moving, the R adapters don't typically add in a whole lot of extra performance overhead. As far as if I've done this with any success, I have implemented a small R adapter just by hand, but I'm not great as far as writing linear algebra code from scratch. So that's something that I need to work on a little bit more. So for larger R adapters, I don't think I would be able to do that without some help. So yeah, definitely a difficult task there and somewhat difficult to implement. But I think someone mentioned this earlier on, but there's a couple of libraries that implement R adapters and things like that. So if you're interested in running this in one of your circuit models, there are some options out there that don't require writing everything from scratch. Okay, so I'm going to move on for now, and then hopefully I'll have time for some more questions at the end. Or if not, then I'll be in the lobby afterwards to answer some more questions. Okay. So I also wanted to talk in some detail about real-time neural networks. I think a lot of people think of neural networks as being these large and slow kind of processes. But more and more now, they're actually being small enough and fast enough that they can be used for real-time tasks, both in audio and in image recognition and things like that. Of course, in audio, we have a bit of a more strict real-time boundary for the things that we're trying to do. So there's a lot more constraints on these systems. So I wanted to kind of go through and show a few neural network architectures that I've seen that can be used for real-time circuit modeling. So let's dig into that. First, there's this method developed by Eero-Pekka Damskog and some other researchers at Aalto University in Finland. Their idea was kind of based on the WaveNet neural network that Google developed, I think back in like 2015 or so. And they call this a temporal convolutional network. So essentially, this is a convolutional network that operates over blocks of samples through time. And they've shown how you can use this neural network for modeling distortion pedal circuits, for modeling tube amp circuits and things like that. And it seems pretty robust and flexible. So definitely a good framework for doing this type of modeling. The one disadvantage is that it's pretty computationally expensive when you're running this in real time. So a couple of things I've seen using this framework. A fellow named Keith Blummer has developed this plugin called Smart Guitar Amp. The demos sound really good. I've seen some of the demos on YouTube, but when I tried playing with it on my machine, it was just a bit too much for my CPU, so I wasn't really able to get much sound out of it. Kind of another cool plugin. This was developed by Christian Steinmetz. He essentially constructed a temporal convolutional network, but instead of training it for modeling some specific circuit, he just uses randomized weights. And you can actually use this for some really neat and interesting distortion effects and things like that. So definitely a cool plugin to check out. Next, Julian Parker and Fabiana Squeda and some other folks at Native Instruments have developed this technique they call state transition networks. This is a bit more of a gray box technique where essentially you look at the circuit and you construct some state space equation that describes the circuit behavior. And then instead of using maybe a Newton-Raphson solver or some other time-consuming solver, they train this pretty small, fully connected neural network for doing these state transitions or these state updates. And this is kind of a neat approach. Actually, Native Instruments claims that their new Guitar Rig 6 plugin is using this technique for some of these little modules they have in here. So that's kind of a neat trick that they've got these neural networks in their plugins now. Finally, this is the architecture that I ended up using for my Klon Centaur model. This is a paper by Alec Wright and a couple other folks at Aalto University again. They use a single layer recurrent neural network, and they've used this for guitar distortion circuits and time varying circuits and so on. So a couple of reasons why I ended up choosing this modeling framework for my circuit model. First of all, it just kind of makes sense to me. So I often try to think about these things from kind of a memory perspective, as far as what memory does the neural network have. For the temporal convolutional network, the network is kind of like an FIR filter in that it only has memory of past input states. For the state transition network, it's a little bit more flexible. The system kind of has whatever memory you give it through the state space equation. But for the recurrent neural network, it's like an IIR filter where you have some past input states if you give it that, and then you have one future state, which comes from kind of the recurrent layer, which I'll show you in a second. So it kind of makes sense to me that if I'm modeling a stateful nonlinear circuit, I should use a stateful nonlinear system like a recurrent neural network. Second, at least compared to the convolutional networks, the RNN is way faster. I think it's like five or more times faster than the convolutional network for equivalent like modeling accuracy. And then finally, Alec Wright showed in his paper how you can actually include control parameters and have the neural network essentially learn how to kind of change what it's doing based on the changing circuit parameters. So this is kind of the signal flow of the recurrent neural network. Basically, what you have here is some input vector. So this could be an input sample. This could be a block of input samples. This could be kind of whatever input samples you want, plus whatever parameter values you want. So they'll all be in this vector, and that's input into your recurrent layer. The recurrent layer spits out the state vector, which is delayed by one sample, and then put back in. So that's similar to kind of an IIR filter in the way that it handles that. And then finally, you also get some output state, which is kind of summed together by this fully connected layer, and then output as a single sample. So unlike the temporal convolutional network where you process blocks of samples at a time, this you have to run every single sample. So you run one sample or one sample time through this input, and you get one sample of output. So you have to run this at every time step. So there's a few different recurrent layers that you can use. Some people use LSTMs. I forget what they stand for, but it's a pretty common type of recurrent layer that you would use. I ended up using this thing called a gated recurrent unit instead, just because it's a little bit faster and a little bit simpler to implement. A couple things to note: they use this sigmoid function here and this tanh function here, and those can be kind of expensive operations that you might see in signal processing from time to time. So to actually model a circuit with this recurrent neural network, I started with the gain stage from the Klon Centaur. So this is a pretty complicated circuit here. They've got these two feed-forward networks along the top and the bottom. You've got this amplifier stage. You've got this diode clipping stage. I think I mentioned earlier, you can also model this stage with a wave digital filter. And then kind of the sum of all these three signal paths here is sent to a summing current amplifier that happens later in the circuit. You've also got these two potentiometers here. These potentiometers are both wired to the gain knob on the faceplate. So they call that ganked potentiometers, where you have one knob controlling two potentiometers. So for actually training the neural network, I started with making about 4 minutes of guitar recordings. I recorded everything at 44.1 kilohertz, which is very low compared to most other kind of neural network training kind of things that I've seen. The reason why I chose this sample rate is that the embedded platform I was targeting ran at 44.1 as well. And for reasons that I'll talk about later, your neural network has to be trained at the same sample rate that you're going to use it at later on. So I split this recording into a bunch of training and validation samples, and then I simulated the output of the gain stage circuit using a SPICE simulation. So as I mentioned at the beginning, the actual pedal is like $3,000, so I couldn't just go out and buy one. So instead, I just used a SPICE simulation. But obviously, if you had the real pedal, that would be preferable. So in order to try to model this gain parameter, I ran my simulations at 5 different positions for the gain knob. And I was hoping that I could train my model to learn this gain parameter as well. So when you're training a neural network, you need some loss function to tell your neural network what kind of the error for your system is, which you're trying to minimize. I ended up using this thing called error to signal ratio, which the folks at Alto seem to really like. And the basic idea here is that your numerator is your mean squared error, and then your denominator is the total energy of your signal. So basically, you're telling the neural network that you need it to be more accurate when the signal is very quiet. So this is especially true if you have times where your output is silent. You want the neural network to output silence also. So kind of coming back to this gain parameter, I was not able to train a network that had learned the gain parameter successfully. I'm not 100% sure why this is. I tried a bunch of different things. It's possible that I was doing something wrong in my training. It's possible that there's just something like special about this parameter that made it very difficult to learn. So I think that kind of this process of training to include parameters needs a bit more kind of research done and a bit more of kind of a robust process for training a circuit parameter into these networks needs to be figured out. But it's kind of a workaround, since I didn't want this to kind of be a stumbling block for me, or at least a blocking thing for me. I decided instead I would train 5 different networks. So for each value of the gain parameter, I trained one neural network for that value. And then when I implemented this in real time, I essentially fade between the different circuit models as you move that knob. So this is what the training kind of looks like. So you see how the training loss and the validation loss are both minimized. So this means the neural network is getting more accurate as you train it for longer. It doesn't really look like there's any overfitting or anything like that. So this is a good sign that our training is working successfully. Next, we can actually look at kind of the waveform level data and see that the circuit simulation from SPICE and the circuit simulation from our neural network are both coming out pretty much the same. We can look at this also in the frequency domain. So you may notice up here there's a little bit of high frequency damping. I'll come back to that later, but it's not super noticeable. So thinking about recurrent neural networks, again, from the perspective of advantages and disadvantages, the big advantage is that compared to other techniques for modeling distortion circuits with black box techniques, it's pretty efficient. It's much more efficient than the temporal convolutional network. That said, as you increase the size of your recurrent neural network, it can become more computationally expensive as well. Finally, as I mentioned, you have to use the same sample rate when you're running inference on your neural network as you do when you're training your neural network. This is especially true for kind of the recurrent neural network, where you have that one sample delay. So, I mean, you can think if you had an IAR filter at one sample rate, and then you change the sample rate without changing the filter coefficients, your IAR filter wouldn't sound right anymore. So you can imagine for these sample rates, that's an important thing to think about. And then finally, I think there needs to be a bit more research into training with control parameters, so that becomes a little bit more fleshed out. Finally, just thinking about computational efficiency. As I mentioned, all of these neural networks, so the dense layers, the recurrent layers, the convolutional layers you might use in a neural network, they often require these nonlinear functions like the tanh function or the sigmoid function. And in signal processing, we know that we can use an approximation like a Padé approximation or a lookup table. And I think there needs to be a bit more research into kind of using these approximations in neural networks, since neural networks are very kind of finicky. And if the accuracy of these functions is off, it can kind of throw off your whole neural network a little bit. So I think that there should be some kind of investigation into like using these approximations, and if it's better to train with your approximation or if it's better to train with the full precision function and then switch to the approximation when you do a real-time implementation. Finally, I think there should be some more kind of research done into correcting for sample rates and figuring out how we can get one neural network to work over a range of sample rates. So I've done some kind of, these are a few things that I've tried to do, but I don't really have any successful outcomes just yet. So that's something that I'm still working on. Okay, so let's see what time we're at here. Okay, I don't want to go over time.
Yeah, you have about 5 more minutes or so.
Okay,
Is that right?
Yeah, I think so. Maybe what I'll do then is I'll not do questions for now, and then I'll
we could
go through the rest of my slides.
We can announce which table you'll want to be on.
Sure.
Yeah, because there'll be like, table 6 on floor 3, something like that.
Yeah, exactly. Yes.
So we'll do something like that. So let's
perfect. Yeah, so I'll go through the rest of my slides here, and then I'll take questions when I'm done with whatever time is left. Cool. So for the real-time implementation, this is the full circuit. So most of these kind of elements of the circuit we've seen before in some respect, but there's the gain potentiometer here, there's the tone potentiometer there, and then there's kind of an output gain or a level potentiometer that's way at the output here. So I ended up making 2 implementations. There is one kind of traditional implementation that uses no machine learning. So I use nodal analysis for some of the circuits and wave digital filters for others. And I was able to handle all 3 control parameters just as parameters to these models here. And then I had a separate implementation that used machine learning. So this is the RNN for the gain stage and nodal analysis everywhere else, just because the other circuits really weren't complicated enough that they required something of that caliber. And then for kind of the gain parameter, as I mentioned, I had to fade between different models for this gain control. So for actually running this RNN in real time, I ended up having to write my own kind of gated recurrent unit and dense layer implementations that I could use from C++ and from Juice or generic C++ code. So first I thought about using the TensorFlow Lite library. So they have kind of a neat format that lets you train a model in Python and then export it to this kind of C++ format that can be run on an embedded device. Unfortunately, they don't support recurrent neural networks, or at least not very much quite yet. I was also worried about kind of real-time audio and memory allocation and things like that. But I've been assured by one of the developers for TensorFlow Lite that they don't allocate memory on their real-time threads or anything like that. So you're probably okay. Next, I tried doing an implementation using the Eigen library. So Eigen is a linear algebra library that has a lot of SIMD support for various operations. And this works great on desktop, but for my embedded device, I was not able to get this to compile. So I ended up writing another engine that uses just the standard library. This std inner product function is really, really useful. If you haven't used it before, you should definitely check it out. And this one I was able to compile on my embedded device, so I was very happy with that. So this is the desktop plugin. There's these 3 knobs, and then here you have a box where you can switch between the traditional version and the neural network version. And then this is my not so pretty embedded version. So this is the Teensy 4.0 microcontroller. So I picked the Teensy. The Teensy is part of kind of the Arduino ecosystem, and I picked that because it has this audio shield that you can buy with it. I think together they're about $35. It has pretty high quality audio inputs and outputs and things like that. It also has this Teensy audio library that supports a lot of useful audio functionality. Sorry. So here I've got these input and output jacks, and then I didn't have any knobs at the time when I made this. Shipping was really slow because of COVID. So at the time I took this picture, I just used these buttons for controlling some different parameter mappings that I had set up in the code. Finally, I ran some benchmarks to see kind of what improvement I got from using the neural network, if any. And I was happy to see that the neural network is actually a little bit faster than the traditional model. So here you can see how long it takes to process 1 second of audio for different block sizes. And at every block size, the machine learning version is a little bit faster. So that's nice to see. Finally, just kind of in listening to them, I think they both sound pretty similar. I can tell the difference, but it's not super noticeable on most signals. For things that aren't guitar, you might notice some high frequency damping in the neural network model. This is probably because I only trained on guitar sounds, which, there's pros and cons there. You can train on more sounds, but it might be more difficult to train. But since this was intended to be a guitar pedal, I figure that's probably okay. Plus, I've had some people who say they like that high frequency damping, so who am I to argue? And then finally, the machine learning model is more efficient. So computationally, or even like in like Pro Tools, I'm able to run more instances of the neural network version, which I like. So just a couple takeaways before I close out here. I've introduced 3 different methods for modeling circuits. Nodal analysis is pretty simple. Wave digital filters is very modular. And neural networks are still pretty experimental, and there's a lot of unsolved problems there, but they are very powerful. And I think that there's a great future ahead for modeling circuits with neural networks and things like that. Finally, I think that a lot of people these days who have been developing audio plugins and so on desktop are trying to move into the embedded space as well. And so I kind of noticed a few things that you don't really think about on the desktop world that are very important in embedded. So one is memory management. If you've got like a lot of neural network weights or something like that, you need to be thinking about where you're going to store those on your embedded device. Another is processing power. So the Teensy has a floating point processor, but not everything does. So that's something to think about. And then also price. You can get a more powerful processor, but it's going to cost more as well. So you want your algorithms to be as efficient as possible. And if something like a neural network can help with that, then that's great. Finally, just a few links here. These slides will be shared, but there will be a public link for them. So there's a technical paper that I've written about this, which goes into a bit more of the math and a bit more of the details. There's a link to GitHub here, so you can read the source code or you can download the plugin and try that out. Also, I haven't given any actual audio demos in this presentation, mostly because I don't trust myself to play guitar in front of anyone. So I've made some videos where you can hear how these plugins sound and how the embedded version sounds without having to hear me, or at least see me, mess up the guitar playing in real time. Finally, I wanted to say thanks to a few people. So Pete Warden and the EE292 class at Stanford for helping inspire this project, and to Julia Smith, Kurt, and JJ for helping me learn wave digital filters and get better with that. And also I wanted to say thanks to the ADC folks for putting this conference together. It's been a great experience for me, and they've put in a lot of work to help make this a great experience for everyone. So I'm really thankful for that. And thanks to you all for coming to attend this conference.